Problem 9.73. We have a wheel with a constant angular acceleration, and we're asked to find the, we're asked to verify that the radial acceleration on any interval of acceleration is equal to this quantity, the product of double the angular acceleration, the perpendicular distance from the center, which is the radius r at which the particle moves in its rotation, and the change in the particle's angular position. So how do we get from this to this? Well, first of all, we're again asked to show that the radial acceleration is equal to this. Well, radial acceleration, let's just follow our nose. Radial acceleration is v squared over r, which is r omega squared. The change in the radial acceleration over an interval, where omega I is the initial and omega f the final, excuse me, angular velocity, is, well, the change in r omega squared, which is this. And factoring out r, we write this down. Now, all this should be pretty obvious. Okay, we're asked something about the radial acceleration, and what do? Well, we first say, well, okay, here's the radial acceleration. We define the radial acceleration. Then what's the change in radial acceleration? These are obvious questions that we should ask and answer. Okay, now having done so, we've got to look at this expression and see what can be done with it. Well, what can be done? We can certainly factor out r, which gives us this. And now if our algebra skills are where they ought to be, it's going to immediately occur to us that this can be factored. If this is factored, well, we get this. And what's this? And what's this? Well, this is double the average angular velocity, and this is the change in angular velocity. Now, I emphasize that I've been emphasizing throughout the course that we don't just have a series of equations and formulas, we have insights. Okay? And if you've developed the insights that we've been talking about, that we've tried to develop in this course, you're not going to need to cast around for an equation that tells you this is the change in the angular velocity and this is double the average angular velocity. You'll know that the average angular velocity, again, for constant acceleration, is going to be the average of the initial and final, which will be this divided by 2, so that this is double the average angular velocity. If you're familiar and friendly with all the quantities that are involved in reasoning out uniformly accelerated motion or uniformly accelerated radial motion, angular motion, you'll understand this, and you're going to be much more likely to see this connection. If you're just casting around for formulas, I think you're going to be pretty unlikely to pull out the right ones here. Okay, so anyhow, we replace this with 2 omega bar, this with delta omega, and we get this. Now, what can we do with this? Well, let's think about what omega bar is again, or what its definition is. Well, its definition is the change in position, which is delta theta, divided by the change in time, which is delta t. So that omega bar is, actually, that's not the relationship we want to use. That's an important relationship. But the way never mind, that is the relationship we want to use. It's here. I'm using description of this to talk about this. Kind of expected that I'd written these in order, and I didn't anyhow. Excuse a little lapse there. But okay, delta omega bar is just what I said, the average rate of change of angular position with respect to clock time. And delta omega is what? Well, what's the definition of delta omega? Well, it's a change in omega. It's also related to the definition of angular acceleration, which is delta omega over delta t. so that delta omega is equal to alpha times delta t. Now, it should be, at this point, people started to see what's going on. If we, I think somebody contributed to the chat with a comment that, oh, the delta t's are going to cancel out, which pretty much indicates to me that they see what's happening. So if we substitute this for omega bar and this for delta omega, we see that we're going to have a delta t here and delta t in the denominator here. They divide out and leave us alpha and delta theta. So that this expression becomes this expression, and there we have it. We never tried to get this expression. All we did was we defined the radial acceleration and looked at what the change in radial acceleration did. Then we made a couple of connections that not everybody's going to make. It's a pretty challenging problem, but if your algebra skills are good and you continue, and if you understand deeply these relationships, the definitions of angular velocity, angular acceleration, etc., average angular velocity, you make this connection, you get this, and boom, there you have what you're after. Okay, so it follows that, well, I did make this connection here. I did do the substitution. So the change in radial acceleration is this, which is expressed as this, which gives you this. Okay, and that is a kind of a neat result. Now, there's things you're supposed to do with that result in the solution of problem 973, but that's one way of obtaining the result. There are other ways, and we might, given the constraints of time, don't know if we will, but we might well talk about those too.